welcome back. Today we've got some really important chemistry concepts we're going to talk about. The first one is valence electrons. Now, valence electrons are the electrons found in the outer shell. Okay, so that's really important, and I want to skip ahead when we talk about outer shells. Once again, the four electron orbital shells are S, P, D, and F. And once again, the word that we use there is speed fighter. Now, if this works for you, great. If not, just remember S, P, D, and F. Get you an acronym for that, or however you want to do it. But whenever you say the word speed fighter, what you hear is S, P, D, and F. It seems like the speed fighter. You just hear those letters accented. So speed fighter, S, P, D, and F. Those are the four orbitals. Now, what we're talking about here, we talk about valence electrons. Once again, we're looking at the exact structure that we talked about a little bit earlier. The nucleus has the protons and the neutrons, and then the electrons are in these orbitals. So remember that the s orbitals travel right around the nucleus here. Okay, the p orbitals come back. And excuse me, and they're kind of three-dimensional. And so what happens is it's actually more than three-dimensional. It's more like six-dimensional. So here goes the p orbital. Here goes this electron. It goes out, and then gravity pulls it out. It goes out, and gravity pulls it out. It goes out, and gravity pulls it back. So keep in mind that the s orbitals, okay, are right next to the nucleus. The p orbitals are coming out, but they always come back. So the s's and the p's are the only ones that are attached to the nucleus. Remember that the d's and the f orbitals are on the sides, so they're not actually attached to the nucleus itself. So when we talk about valence electrons, we're talking about electrons in the outer shell, the ones that can actually bond with something. So the only valence electrons we have are the s's and the p's. Oh, okay. So valence electrons, electrons in the outer shell, we'll talk about that more as we go. I want to just introduce this to you. Right now, you don't need to know this so much, but I want to introduce this. Okay? So everything in group 1 ends in S1, okay? Which means that it has one valence electron. Everything in group 2 ends in S2. It has two valence electrons. Now, these are the transition metals. We'll come back and talk about those later, okay? So this is a neat way that the chemist, let me grab my yardstick here, my meter stick. And so everything in this group ends in S1. Oh, how many valence electrons? One. How cool is that? Group 1 has one valence electron. Okay? Now, you got to remember, you got to think like chemists. Chemists are trying to simplify things, make things easy. It's not about making things complicated. It's about making them black and white. Not real opinionated, just very simple and easy to go. So everything in group 1 has one valence electron. Everything in group 2 ends in S2, so it has two valence electrons, because the most s's we can have in an orbital is 2. And once again, these are transition metals. We'll talk about them later. They either end in an S1 or an S2. Now, isn't that cool the way we have this as chemists? S1s, S2s. One valence electron, two valence electrons. Drop down, transition metals. Oh, that's cool, okay? Now, then we come up over here, and if you look, we have 1, 2, 3, 4, 5, and 6. These are the p orbitals. Everything in group 13 ends in a P1, okay? Which means that for valence electrons, it has an S1, an S2, and a P1. Ah, cool. Well, look what we have. Group 13 has 3 valence electrons. Group 14 ends in a P2, plus the 2 S2 it has 4 valence electrons. So we see the pattern. All of the teens tell us how many valence electrons it has. 13 has 3. 14 has 4, 15 has 5, 16 has 6, 17 has 7, and 18 has 8. So that's really cool. So when we talk about valence electrons, we'll want to know that because those are the only electrons that can bond with another element to make a compound. So that's just a quick introduction to valence electrons. We'll come back. We'll talk about this a little bit later. And I just wanted to introduce that to you, but there's some neat things we'll learn. We're fixing to be on the periodic table and determine bonding and bonding sites. So we're going to move on, and we're going to start talking about pH here. Now, pH, it's a little p and a capital H, because this is a Latin word, and the P is actually for hydrogen, and it's kind of an interesting deal. The capital H, okay, the capital H stands for hydrogen, okay, and since it's the element hydrogen, it's capital H. So pH is actually a measure of the hydrogen ion concentration. All right, so an acid has a pH of less than 7, okay? A base has a pH of more than 7, and pH 7 is neutral. And once again, we'll talk more about pH too. It's just a quick introduction. Now, let's talk about some of the terms that we're going to have in chemistry. Monoatomic, of course, once again, prefix mono meaning one. Monoatomic is one atom. Diatomic, prefix di meaning two atoms. Polyatomic, poly meaning many, 3 or more atoms. When we talk about qualitative versus quantitative, quality, how good something is, what it's made up of. Qualitative tells us which elements. Qualitative tells us which elements. Quantitative, how much of each element. All right. So if we're looking, once again, if we're looking at water, okay, if we're looking at water, H2O, all right, just going to take a simple one here, okay. So I want to do a qualitative study on this, okay. I want to look at the quality. What's water made up of? Well, it's made up of hydrogens, it's made up of oxygens. I want to do a quantitative study. Oh, it's a 2-to-1 ratio. I have 2 hydrogens for every oxygen, okay? How much of each element? Qualitative versus quantitative. And in some of the labs that you have coming up, you'll do a qualitative versus quantitative study on a lot of different chemicals. Now, when we talk about this empirical formula, that's the simplest formula, okay? So, for example, we just look at the same molecule here with water. Water is H2O. If we had something that was, now it's not like a math problem where you're just reducing them. You got to look and you got to say, okay, now do I have one water molecule? If I had H4O2, what I really have, the empirical formula for that is not really H4O2, it's 2 water molecules. So, man. So we'll all stop, take a drink of water. Okay, now here we go. So we look at the empirical formula, simplest formula. Now I don't want you to start reducing all the formulas down. A lot of times I will just ask you, even on the test or even in the lab, they'll say, is there an empirical formula? Is there a way to look at this and maybe say, I have 2 of one particular molecule rather than one big molecule? So you'll see that again later. A lot of the things we're talking about today you will definitely see in your labs. Now, molecular versus structural formula. The molecular formula is a number of each element. So the molecular formula, once again, we just use water throughout this, for example. The molecular formula is H2O. 2 hydrogens, 1 oxygen. Of course, you know that 2 is a subscript down below it, meaning that there's 2 of the preceding element. And if there's no subscript, that means that there's 1 of the element preceding that. So the molecular formula would be H2O, but the structural formula actually shows the bonds. So water, H2O, we have two bonds at 90-degree angles. We will learn later that this is polar. Polar means bent. Okay, water is a bent molecule. All right, and the reason for that is that opposite charges attract. So if one's a positive, one's a minus, they're going to attract as far as they can. It's going to make it a polar molecule. We'll come back and talk about polar and non-polar a little more as well. Now when we say a ternary compound is 3 or more different elements in one compound. A good example here is sulfuric acid, H2SO4. We have hydrogen, sulfur, and oxygen, so we have 3 or more. We meet the criteria for a ternary compound, 3 or more different elements in one compound. Now, once again, as we do these, remember it's kind of nice to be able to go back and re-watch these. We go pretty fast. You can even pause these and take down notes, but that's the beauty of this class. When I'm teaching this in a regular class, somebody will say, hey, Mr. Anderson, could you stop for a minute and can I get this? So this is the beauty. You guys can start and stop this tape anytime you want. So I think you're getting a pretty good deal with this opportunity to be able to take it at your pace. We do go pretty fast in the notes though, because each video downloads about a 20-minute section. So we're trying to keep it within a 20-minute section. So now let's do some chemical prefixes. All right. So 1 is mono, okay, 2 is di, 3 is tri, 4 is tetra, okay. So here we go, let's look at some, okay. CO, this is carbon, and since there's just 1 there, monoxide. Now, we usually don't use mono because we usually know that if there's not a prefix that it's 1. But we do in the case of carbon monoxide. Now, I'm fixing to go into the nomenclature and the naming, we'll talk about this. Now, if I had right here, okay, CO2, that would be carbon dioxide. Carbon dioxide. All right? And if I won't do O3 there because that's a whole different name. But if we had N3 3, okay? Well, let's don't do that one either. Let's do this one. Let's say, let's take I3, that would be triiodide, okay? And then we have a really famous one for tetra, CCl4 is carbon tetrachloride. And we're fixing to do the naming in the very next part of this unit, so I'm excited to get to that. But we'll definitely use those prefixes as we go. Now, then we talk about some Latin prefixes, okay? More than, the Latin word for more than is per, okay? And then less than is hyper, all right? So if it's more than, for example, we're going to talk about hydrogen peroxide, okay? H2O2, all right? That's kind of interesting. What they're saying is that's more than water. Water is H2O, but we have an extra oxygen, so we're saying in the Latin prefix hydrogen peroxide, it means it's more than the oxygen that's in water, okay? And less than is hyper. We hear things like hypertonic, hyper solution. It means it's less than the original solution. So once again, what we tried to do at the beginning of this is try to define a lot of the terms that are used in the chemical analysis and in naming chemicals. Now, we're going to go to the next video is going to be on nomenclature and naming. And so fasten your seatbelt and we'll be right on that next.